nice morning, isn't it? Sun's out, finally. I didn't get a chance to go outside yet. So it's kind of unusual. I have a whole house full of people today. Of course, my wife is here. But also, my 16-year-old is sick. He's been sick for a few days. Just a fever. Don't know what brought that on. And then my youngest son got word yesterday that someone at his school had coronavirus, and he was potentially exposed. So now he's home. So, just a little unusual. Let me get some cameos from some boys popping in here. How are the rest of you?
Doing good.
Yeah.
Another beautiful morning.
It is. So, like last time, I think this might become a more permanent feature. I'm also simultaneously streaming this to YouTube. Now, they can hear you, but they can't see you. So, they can see me, obviously, but they can't see you. But occasionally I may look at the chat on YouTube and they might have something to say, and I'll bring that into the discussion. So when we left off last time, we were talking about a Bayes rule. And I thought I would start off with a couple of warm-up questions. So these are for problems for you to figure out. And then we'll go over the answer. Why don't we just do the first problem first, and then we'll work on the second one. So in the first question, we got this barrel of balls over here that have a whole bunch of balls thrown in them. And if you were to pick out a ball at random, there's a 0.2 probability that the ball you'll pick is red, a 0.28 that it's blue, and a 0.31 that it is yellow. What is the probability that the ball you're going to pick is green? Okay, so I saw someone in the chat actually put the calculation in there. What does the answer come out to be?
0.21.
Yes, 0.21. And we can get that by just doing 1 minus 0.2, and then minus 0.28, and minus 0.31. Okay, problem number 2. We have this diagram showing that event Y causes event X, and the probability that Y will occur is 0.4. The probability that X will occur given that Y occurred is 0.1, and the probability that X will occur given that Y did not occur is 0.2. What's the probability that Y will occur given X? Or I should say, what's the probability that Y did occur given X? So if you remember from last time, there's that tree diagram. You might want to start out by drawing that diagram, and then on that diagram there's going to be 6 numbers, or 6 places to put numbers. I will usually give you 3 of them, so you need to come up with the other 3. And then, since the probabilities were given as X given Y, but we want to calculate Y given X, Bayes' rule is great for switching those around. So you'll want to apply Bayes' rule for this one. So maybe I'll give you a minute to work on this. Anybody got an answer yet?
No, I just drew my trees wrong.
Uh-oh. Maybe if you're working along, you can put in the chat, what are the other 3 numbers that you would write over here? So if we have the probability of y, what's the other number that you would put over here? Good. Good. We would put the probability of not y, 0.6. And from this diagram, y causes x. We can see the arrow is pointing toward the x, which means that y is going to come first in our tree, and then x is going to come after that. What are the other 2 numbers?
Just give me something so I can move on. Pull me closer or push me away.
Yes, 0.9 and 0.8. So this one, what is the probability? It's the probability of what equals 0.9, and the probability of what is 0.8.
Not x given y, and then not x given not y.
Good. So in order to figure out what probability to write over here, you just take this one on the left-hand side and not the very first variable. We can kind of label the tree here with those probabilities. I'll put the numbers in, but this first branch is the probability of x, and the other branch is the probability of not x. Oops, not x. I didn't mean x, I meant y. And then the very topmost branch is the probability of x given y. And below that is the probability of not x given y. And then down below we have the probability of x given not y, and the probability of not x given not y. So those are our 4 possibilities. And then we'll put in the numbers. We've got 0.4 and 0.6. Then we have 0.1 up here, 0.9 down below, 0.2, and 0.8. So those are the 6 numbers in our tree. Now we want to calculate the probability of y given x. So we'll use Bayes' rule for that. Which is the probability of y given x is equal to the probability of x given y times the probability of y over the probability of x. All right, we know the top, we know the numerator, that's 0.1 times 0.4, and then the denominator we're going to need the probability of x, which we can get to by this branch and this branch. Those both end up with the probability of x's. Okay, so that'll be 0.4 times 0.1. I just just did this right here. And then plus 0.6 times 0.8. That was, oh no, not
0.2.
0.2. Yeah, thank you. I'm looking in the wrong place in the tree. Okay, I just did this one here. Okay, numerator is 0.04 and denominator is 0.16, which is 0.25. Okay, let's do another problem. Similar setup, different variables. So let's start filling out these other three numbers. Let's draw our tree over here. Solve the problem. Okay, the other three numbers are the probability of not A is 0.63. The probability of not B given A is 0.27. And the probability of B given not A is 0.88. Notice again that the probabilities are given as B given A, but I want to calculate A given B. So the variables are reversed, which means this is a good application for Bayes' rule. I'm going to write it in there. You know, this is how I ended up memorizing Bayes' rule myself. Is I look at what we're trying to calculate. First thing I do is I just flip the order. So this is A given not B. The first probability is going to be not B given A. So I just reverse those. And then the probability that goes over here on the right-hand side is just the same as the variable on the given side of the previous probability. So whatever variable is right here, that also goes over there. And then the remaining variable goes down below. So it's just a pattern that I've memorized in the years that I've done this. Flip the order around, then the second variable goes over here on the right, and the first variable goes down here on the bottom. Sean, you think your answer is 0.21?
I think, but I'm always doubtful.
Oh. I wasn't sure if what we were posting there was the final answer or one of the probabilities. Well, let's see how we do. So let's before we start plugging in the numbers, I want to expand this out, because this bottom one is always the one that's hard to calculate. Not like impossible to calculate, but it's hard because there's no just probability of not B sitting there in the numbers that I've given you. You have to calculate that by looking at the tree. First, let's just write it. Let's expand everything out. I think that'll be helpful. So we'll do probability of not B given A times the probability of A. And then on the bottom, in order to find not B, the probability of not B, we're going to be following this branch and this branch. So that's going to be the probability of A times the probability of not B given A, that's that top branch, plus the probability of not A times the probability of not B given not A. That's that bottom branch. Now we can plug in the numbers. Not B given A is 0.27. Probability of A is 0.37. We've got our numerator done. And then for the denominator, we have the probability of A, 0.37, times the probability of not B given A, 0.27, plus 0.63 times 0.12. Right, so this number came from here, and this number came from here. So if we run that through our calculator, let me go ahead and do that. So we have 0.27 and 0.37 gives us 0.0999. And then down at the bottom we have 0.0999 plus 0.63 and 0.12 is 0.0756. And then we'll add the bottom numbers together. And we get 0.1755. And then finally we'll divide. And we get 0.569. Okay. Now, I kind of brought up here a moment ago that when you're calculating this denominator down here, it gets a little complicated because there's all those branches of the tree. And right now, all we're dealing with is a single kind of starting variable and then some follow-on variables. So there's only a total of 6 numbers in the tree. But if we had more things in there, the tree would get a lot more complicated. It would be more branches. Possibly the tree would be deeper. And so that denominator is going to get more complicated to calculate. So I want to show you, now that you have some experience using Bayes' rule, I want to show you how to calculate Bayes' rule, but using a table rather than, a huge numerator and denominator. What the table is going to allow you to do is, first of all, to organize your numbers a little bit better. But secondly, it's going to allow you to calculate more complex probabilities without a whole lot of extra space. So let's do the same problem, same numbers, but I'm going to show you how to do it with a table. So over here is Bayes' rule. This probability right here, the one over on the right-hand side, has a name. It's called the prior, because it's the event that happened first. You can tell it's the prior because it's at the top of our diagram. It causes all the other things to happen. So we already know what the answer is going to be. We know the answer is going to be 0.569, right? So we're aiming towards that. We'll know we got this correct if we end up with the same answer. But let's set up this table. So I'm going to do it like this. I'm going to label my columns. The first column will be labeled prior. And then down the left-hand side, I'm going to put that variable that's the prior, A and not A. And then in the next column, I'm going to put my dependent variable, the one that I'm trying to calculate. So my dependent variable is not B. So I'm going to put that one there. And then I'm going to have another column I'm going to label P prime. This is called my, going to be like my partial probability. It's not my full probability. It's going to be an intermediate calculation. And then finally on the right-hand side, I'm going to put P, which is my final probability. Okay, in the prior column, I'm going to put the probability of A and the probability of not A. So I'm going to put those numbers in there. In the next column, I'm going to put the probability of not B given A. So it's kind of like the intersection of these two variables, not B and A. And below that, I'm going to put the probability of not B given not A. I'm going to multiply those together. And I'm going to get a number here. And I'm going to get a number here. I'm then going to add those two numbers together and get a third number. Okay, so this first number, I'm going to copy over to my P column, and then I'm going to divide that by that sum number, this one over here. And that's going to be my answer, which is the probability of A given not B. Okay, that's how you set up the table. Now let's put the numbers in. So let me just redraw the table down here. Got my prior column, A and not A, not B column, P prime column, and P column. Okay, in the prior column, here I'm going to put the probability of A, which I've got, 0.37. And the not A, which is just 1 minus that number. Under the not B column, I'm going to put the probability of not B given A, which is not B given A, which is right here, 0.27. And then down below that, I'm going to put the probability of not B given not A, which is right here, 0.12. Multiply those together. And I get 0.0999. And then when I multiply the other two together, I get 0.0756. Then I'm going to add those together, and I get 0.1755. Okay, last step. 0.0999 divided by 0.1755. So I just brought this number over, and I brought this number up. Then when I do the calculation on my calculator, I already know I'm going to get the same answer. I'm going to get 0.569. Okay, the thing I want you to notice is what numbers are in that table. So we've got 0.0999 right there. We got 0.0756 and 0.1755. And if you look over on the previous screen, those are the same numbers that we've got here. And then we end up with the denominator here, the numerator here, and then our final answer. So this is the numerator from the previous slide. And the 0.1755 is the denominator from the previous slide as well. So this table ends up calculating all the same values, but in a nice compact form. And notice that we didn't need to draw the tree either. So one of the cool things about Bayes' rule is it allows you to calculate actually all these wacky probabilities. You know, like I could start with some precondition like it's cold outside. And that might cause me to wear a sweater and want to drink some soup. So I could calculate probabilities like, what's the probability that I'm going to wear a sweater given that it's cold outside? Or what's the probability I'm going to want to drink some soup given that it's cold outside? But I could also flip those around. I could calculate what's the probability that it's cold outside given that I'm wearing a sweater? And what's the probability that that it's cold outside given that I'm drinking soup? So I can actually calculate both probabilities. And I can even do more wacky stuff. Like if I'm wearing a sweater, what's the probability I'm also drinking soup? And I can do stuff, I can even reverse the diagram. Like, you know, if I get a raise, let's say, you know, that causes me to be happy. And if I'm eating a cookie, that also causes me to be happy. Okay, so I can calculate things like, if I know the probability of me getting a raise, what's the probability I'm also going to be happy? And I can calculate if I'm eating a cookie, what's the probability I'm going to be happy? But I can also flip those around. Like, if I'm happy, what's the probability I just got a raise? And if I'm happy, what's the probability I just ate a cookie? And even more weirdly, if I'm eating a cookie, what's the probability I'm going to get a raise? You can calculate all this stuff with Bayes' rule. You just draw these really wacky diagrams, right? As long as you know what variables are causing other variables. You can calculate all these probabilities if you know what the probabilities are. I mean, if you know what these individual probabilities are, you can calculate all these probabilities and even, you know, work your way through the tree. You know, if this thing is happening, what's the probability this other thing happened or will happen? It's very cool. Eat more cookies.
So the happy one brought up a question for me that actually I was thinking about a few problems back, which is, is there a way to include in Bayes' rule like ambiguity there? Because you could be happy for any number of reasons that weren't a raise or a cookie.
Mm-hmm.
So we would have incomplete probabilities for happy, right? It wouldn't add up to 1 with just raise and cookie. You see what I'm saying? Is there a way to incorporate, like, would you just throw in another variable there? And
Yeah, I think in order to do these calculations, you need to know all the variables that are influencing these things. I mean, certainly, I'm just speculating here that there might be, another variable that we don't know that's also influencing my happiness. But let's say it's just not involved in the calculations, right? Like, I know the probability of getting a raise. I know the probability of eating a cookie. There's this other thing out there which I don't know what it is. But I could say, like, the chances of me getting a raise is 1 out of 365. The chance of me eating a cookie is like, what, 1 in 7. And there's this other thing out there that's also influencing my happiness, but because it's not something I'm concerned about when I'm doing the calculations, maybe I can, leave this one out. I know what its probability is, right? Because, do I know what its probability is? So anyway, that's something to think about, is like, can you leave something out and just not include it in the calculations? Like, you probably can.
Well, because then if you were to say, if you were to calculate the probability that it was the raise or the cookie that made you happy, you would be missing a whole chunk of other possibilities.
So you're saying,
which seems like it would positively skew those numbers.
Yeah, like, are these the only 2 things that influence my happiness versus some other thing? I don't have a good answer for you right now, but it'd be something to think about.
Professor, is there a limit of things that we can have in the calculation? Number of factors?
I can barely hear you. You're breaking up and really quiet.
Can you hear me now?
Yeah, that's better.
Yeah. Okay. Is there a limit to the number of factors in the calculations? Like
No.
how many things we can calculate?
No.
Okay.
Not at all. In fact, that's what I'm going to show you next, is how can we incorporate some more things into this. So, you remember those cancer calculations we did last time, where we did the tree, and we did Bayes' rule? I want to do that exact same problem, but using the table instead of the tree and the Bayes' rule directly. So, first thing we're going to do, we've got 3 numbers. We're going to put in the other 3. Oh, I messed up right there. Okay, let's set up the table. So my prior is you either have cancer or you don't have cancer. We wanted to calculate what's the probability of having cancer given that the test we did came out positive. So that's going to be our next column, the positive column. We've got our P prime column and our P column. All right, let's throw the numbers in there. The probability of having cancer is 0.01 and not cancer is 0.99. The probability of a positive test given that you have cancer is 0.9. And the probability of a positive test given that you don't have cancer is 0.2. Then we're going to multiply those together. And we get 0.009 and 0.198. Add them up. We get 0.207. So our final answer is 0.009 divided by 0.207, which is 0.043. That's the same answer we came up with last time. So just setting up the same problem, but using a table instead. Okay, so last time I asked, what do you think about that number? So you went to the hospital, you didn't feel too good. Doctor did a test, came back positive, and now has run the numbers. You probably, while you were waiting for the test to come back, you ran the numbers too. And it turns out that the probability you have cancer is 0.04, so about a 4% chance that you do, which is, not that high, but, still it's cancer, right? So you're probably thinking, well, let's do the test again. The doctor probably agrees. Let's run the test again. So we're going to run the same test, the exact same test, so same probabilities. We're just going to do it again to kind of get a confirmation. So in this case, we got a picture that looks like this. We got cancer as our prior. Then we ran that first test. And then we're going to run the test again. Same test, but just twice. So the picture looks like this because the cancer is influencing the outcomes of the tests. But there's no connection between the tests. The outcome of one test does not influence the outcome of another test. The fact that we got a positive the first time does not change whether or not we get a positive the second time. So here's where the table is really going to pay off. We have the same prior, cancer and not cancer. But now we have two positive tests. Oh, this is what we want to do, is what's the probability that we have cancer? We run the test again, and it comes back positive also. Okay, so we ran the first test, came back positive. Ran the second test, it also came back positive. Oh, John actually asked that exact question. How might we calculate cancer given positive case? That's exactly what we're going to do. Okay, so we have two positives here. We have our P prime and our P. So let's put the numbers in, 0.01 and 0.99. Those are the same numbers from above. The positive numbers here are 0.9 and 0.2. And then the same numbers again. Multiply. And then we get 0.01, 0.9, and 0.9. And that's 0.0081. And then on the bottom, we've got 0.99, 0.2, and 0.2. And we get 0.0396. Then we're going to add those together. And we get, what do we get? 0.0477. Okay? And then finally, we're going to do 0.0081 divided by 0.0477. And that gives us 0.16. 0.9, actually 0.17. Okay, so test came out positive twice. Probability of having cancer is 0.17. What do you think about that number? Did the probability go up a lot? Did it go up a little?
Went up by 200%.
200%? Almost 400%.
Yeah.
So, test came back positive. You now are like 4 times more likely to have cancer. It's still not like half and half, but it's still a lot more likely. John points out, double positives should reinforce the diagnosis. Certainly. Right, you get 2 positives, that confirms it. But now we've got hard numbers, right? It's not like it doubles the probability you got cancer. It's 4 times as likely. Okay, let's say a different scenario occurred. Let's say the first test came back positive. We run the second test, but that one comes back negative. What are the probabilities now? Well, our table let us calculate that. So our prior numbers are the same. The positive numbers are the same. But the negative numbers are different, obviously. So we have the probability of a negative test given that we have cancer, which is this number here. And then the probability of a negative test given that we don't have cancer, which is this number. Multiply those across. Uh, 0.01, 0.9, and 0.1. Zero point zero 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 9, 3 zeros. And then on the bottom we have 0.99, 0.2, and 0.8. And we get 0.1584. And we're going to add those together. .1593. Okay, for our final probability, we've got 0.0009 divided by 0.1593. And that gives us 0.0056. Wow. What do you think about that number?
My first thought is I'm curious if it's higher or lower than if we just got one negative test back in the first place.
Oh, and what are you finding?
I might have that calculation on here still, but I'm gonna have to dig for it for a second.
So the calculation we've got on the screen here is first test came back positive, second test came back negative. So we got one positive test, one negative test. And the probability is now 0.0056. So it's about 1/10, approximately 1/10 of what it was to begin with. And what we want to do is compare that against what's the probability of having cancer given the test just came out negative to begin with. So I'm trying to imagine that scenario. Let's say you walk into the doctor's office, you don't feel very well, they run a test for cancer, it comes back negative. If the probability is pretty low, they might just, send you on your way. How does that compare with running the test twice?
I got like a smaller chance for running of cancer. It's 0.00126 is what I got.
So about 4 times smaller than this number.
Yep.
Yeah, so if you just got that negative diagnosis to begin with, probably would have just sent you home, right? 1/10 of 1%. It's pretty small. Even with this, it's still pretty small. So we get back that negative test, probably look for other causes. Or could be, kind of the naive approach is like, well, this is inconclusive, right? We got a positive test and we got a negative test. It's the fact that most people don't have this cancer that really influences the numbers that we're getting. So most people would say like, well, it's inconclusive, right? We got one positive, we got one negative. But really, the conclusion is it's a very small chance you've got the cancer. But I would say most humans would say, well, let's run a third test, but maybe let's not use the same test again. Let's use some different test. See what we get. But I want to move on a little bit. I promised you that this was all going to have to do with spam filtering and how spam filters work. Email comes in and it gets analyzed for the potential that it is spam. How does that analysis happen? In the past, it would have done pattern matching. It would have looked for common words or common phrases that spam messages tend to have. And then each one of those phrases would probably get some kind of score associated with it. And then if the score went over a certain threshold, if you summed up all those scores and went over a certain threshold, then it would mark that message as being spam. And if it didn't meet that threshold, then it would go into your inbox. But the problem with that approach, which is probably 20 or 30 years old, was that the phrases are always changing in the spam messages. And in fact, the spammers run their messages through those filters in order to see whether they get caught or not. And if they do get caught, they change the wording a little bit and run it through the filter again. And if it doesn't get caught, then they go, great, let's send that one out. But the Bayesian spam filters have the nice feature of being able to learn over time what is and isn't spam. And in fact, when you go into your email program or email website and you see a message that you know is spam, but it appeared in your inbox, it just means that it slipped past the filter. And usually there's a button on the screen somewhere that says mark this as spam. Then it takes that message and puts it in the spam box. And from that information, the spam filter is now able to learn some additional things about messages that look like spam. And the fact that you kept messages in your inbox means that those are the ham messages. Those are the ones you want to keep. If you go into your spam box and you see a message there that shouldn't have been marked as spam, you move it back to your inbox. Again, the spam filter learns from that this is what ham messages look like and this is what spam messages look like. So whenever you move messages around, you are teaching the spam filter to do a better job in the future. Okay, so if you want the spam filter to work as best as possible, not only, you probably shouldn't, if you see a message in your inbox, you shouldn't just delete it. Move it, mark it as spam, move it in the spam folder, and then the spam filter will learn from that. That's what spam messages look like. So to a spam filter, an email message, or I should say to a Bayesian spam filter, an email message is not like a specific set of words in a specific order. It's just a bag, a set of words. So even if your message is something like, hello, I will say hello, which is a totally nonsense message, right? It doesn't consider into this at all the order of the words. It just calculates statistics on what words appear in the message. And it builds up something called a dictionary. So in this dictionary, the word hello appears twice. I appears once, will appears once, and say appears once. Also, the thing to keep in mind about these spam filters is they don't know anything about English or whatever language they're studying. They don't know anything about the grammar. They don't know anything about the vocabulary. All they look at is the words that it sees. Any word that doesn't appear in its corpus of messages to look at just simply doesn't exist. It doesn't have a dictionary. It doesn't have a real dictionary, like one that has a comprehensive list of all possible words. All it has from the dictionary that's building is the words that it sees. So if this message with these 5 words, was the only message that the spam filter had ever seen in its entire life, then it calculates probabilities based upon just that one message. For example, what's the probability that some given word is the word hello? And remember, the only message this spam filter has ever seen is this one. So what's the probability that a given word is the word hello?
2 out of 5.
2 out of 5, good. What's the probability that a given word is the word will?
1 out of 5, and it's the same for the rest.
Yeah, 1 out of 5, 0.2. What's the probability that a given word is the word today?
Zero out of 5.
0, right? The word today does not exist in its vocabulary at all. Okay, so let's feed the spam filter some more messages. Now, when you initially kick it off, what you're going to do is feed it some messages, and a human's going to go through and mark these messages as either spam or ham. So you kind of get a human to kind of start teaching it. And what we've got here is some messages, and each one of these lines here is a message, right? I'm keeping things short and simple here. So each message here is just 3 words. So we've got some messages that are marked as spam, and we've got some messages that are marked as ham. How many total messages are there?
8.
8, good. How many distinct words are present here? In other words, how big is the dictionary?
6 on the left. 6 under spam. I don't know, this is hard to count.
I know, it is. I'll let you, there's 12 distinct words in there. There's a lot of repeats. How many words are there in total?
24.
24? How many total words are on the spam side? One, two, three, 4, 5, 6, 7, 8, 9. How many total words are on the ham side?
15.
15. Good. What's the probability that a given email message is going to be spam?
9 out of 24.
No? There's a total of...
Oh yeah, 3 out of 8.
Yes, 3 out of 8. And so the probability that a given email message is ham is 5 out of 8. Okay. if a message if we know a message is spam, what's the probability that a given word is going to be the word secret?
Three out of 9.
Good, 3 out of 9. So if we know the message is spam, which means we're only looking at the left-hand side here, 3 out of 9 words are the word secret. And if we know the message is ham, what's the probability that a given word is the word secret?
1/15.
Good, 1/15. Okay, let's flip that around. If we have a word sports, what's the probability that that message is a spam message?
1 in 9.
No? Well, we're going to need Bayes' rule for this. Right? We know how to calculate these probabilities. Those are easy. This one here, it's switched around. So Bayes' rule will help us work with that switch.
From just the data without Bayes' rule, can we not say that it's 1 out of 6?
It is actually 1 out of 6. You're right. But let's see how we would apply Bayes' rule to this, which is what the spam filter would actually do. Okay, so we've got the probability of the word sports given that the message is spam times the probability of spam over the probability of the word sports appearing. Okay, sports given spam. So if we look on the spam side, sports appears 1 out of 9 times. And we already know the probability of spam is 3 out of 8. And then in the denominator, we just need to know what's the probability that a given word is the word sports overall. And so sports appears 1, 2, 3, 4, 5, 6 times, and there's a total of 24 words. And if you work out all those calculations, you get 1/6. Okay, so if a message comes in and it's just the word sports, that's it, that's the entire message, right? It's just the word sports. There's a 1 in 6 chance that it's actually spam. But let's see what happens if a message comes in and it's the word secret. So we're going to use Bayes' rule for this, but let's set up a table. Got our prior. Secret is our next column, and we have our P prime and P. And our prior is the message is either spam or ham. Or another way to say is it's either ham or not ham. Or spam or not spam. Okay, there's a 3 out of 8 chance that it's spam and a 5 out of 8 chance that it's ham. Actually, I'm just going to go ahead and do this as decimal numbers. Let's see, 3 out of 8 is 0.375, and 5 out of 8 is 0.625. 0.625 if I do my calculation correctly. Let me. Yeah, 0.625. Secret is, well, let's see. Secret given that it's spam. 1, 2, 3. It appears 3 times out of a total of 9 words. So that's 3/9, which is 1/3, which is 0.333. And then secret given ham. Secret appears just once. So 1 out of 15 times. Is, oh boy, 0.067. I think I got that right. Multiply. Okay, 0.375 and 0.333. We get 0.1248. And then 0.625 and 0.0667. I'm going to multiply those, and we get 0.0417. Add those up. $0.166 I think. And then finally we get 0.1248 divided by 0.1667, and we get 0.75. Okay, so if a message comes in and it's just the word secret, there is a 3 out of 4 chance that this message is spam. But now, given our table, we can expand this out to include more complex messages. Including messages that we've never seen before. So here's the message, secret is secret, right? It's not one of the messages we've seen on the ham side, it's not one of the messages we've seen on the spam side, but we can compute the probability that this is spam with the information that we do know. Let's set up our table. Okay, we know some of these numbers already, 0.375 and 0.625. Secret is 0.333 and 0.0667. Same thing under the other secret column. And then for is right here. Let's see, is given spam. It appears once, so that's 1 out of 9. 1 out of 9 is 0.111. And then is given ham. Well, it appears once, so it's 1 out of 15. So that is also 0.0667. Okay, let's multiply all the way across. And I get 0.00463. And then the other one, 0.625. And I get, whoa, that's a small number, 0.000185. Add those up. Zero point zero zero 4.8. I'm going to round here. 4.82, I guess. Okay, 0.00463 divided by 0.00482. And I get, whoa, 0.96. If I round a little bit. Okay, so the message comes in and the message is secret. There is a 0.96 or 96% chance that this message is spam. Remember, this is all just based upon the messages it has seen before, which are just these 8 messages. So its entire world consists of just these 8 messages, just these 15 words. Or 12 words. So we might say that this message goes over that threshold and we're going to throw that into the spam box. Okay, so hopefully that gives you a little bit of insight into how these spam filters work. They analyze a corpus of ham messages, analyze a corpus of spam messages, and a human has probably gone through and marked these as being either ham or spam. And then it compiles all these statistics about those messages, and it can use those stats to calculate whether a new message that it has never seen before is either spam or ham. So that's really one of the great things about this style of filtering, is that it's able to adapt to new messages coming in based upon things it has seen in the past. And again, humans are helping it out by moving messages into the spam filter or their inbox when it makes the wrong decision. So we'll do one more calculation. The message to come in is, today is secret. What's the probability that it's spam? So we'll set up our table. Okay, spam is 0.375 and ham is 0.625. Today, given spam, is, well, today never appears. So we got a 0 there. And that's actually a little bit of a problem, because when we multiply these together, we're going to get 0 here. And then when we compute our final probability, it's going to be 0 divided by something, right? Remember, we're going to add these up. but we're going to end up with 0 as our answer. So here's a problem with it, is if a word comes in that it has never seen before, it can cause the calculations to drop to 0. That can throw off the filter, obviously, because this message clearly contains words that do appear in spam, but the fact that there is a message that is never seen before, a word that is never seen before, causes all the calculations to just drop to 0. So the answer is, in practice, there's a neat little trick that it does. It uses a technique called Laplace smoothing. The way that works, and it's really easy to do, is for every single number that you calculate, just add a very small constant to it, like 0.00001. That way, none of these numbers that you put in here are ever 0. They're always going to be at least some very small positive number. So that when you multiply them across, you don't end up with 0, ever. You end up with potentially a very small number. But then you factor out that number when you're done at the end. So you add a small constant to all the numbers, and then you factor that number out when you're done with your calculation. And that way you never end up with exactly 0. So Bayesian filtering ultimately is just one of many techniques that spam filters use. They don't just use this because it can be thrown off a little bit. There are other criteria that a spam filter would look at to determine if a particular message was spam or not. For example, did the message come from a known spammer? Now, most spammers get around this pretty easily by just putting in the from message someone that is known not to be a spammer. And there used to be, it's a lot less common now, but it used to be, it was fairly easy to get some malware onto your computer. And then what that malware would do is just go through your contacts list and then send off to the spammer every email message and name that it could find on your computer. And then when a spam came to you, it would appear to be from someone you knew. And that would throw off the spam filters, because a lot of the spam filters these days, if the message comes from someone you know, it just throws it right into your inbox. And to get around this problem, maybe the first time a message comes from someone you don't know, it throws it into the spam box, or it flags it for review. But then if you mark it as, like, this message is okay, then it just goes straight in your inbox. Or I think what a lot of them do is, if a message comes in 3 times in a row from the same person, it just assumes that you know this person. So if it sees the same sender 3 times, then it figures this is someone you know, and just throws it straight into your inbox. Another would be is a file attached. Particularly if the entire contents of the email message was just a file. This is a technique spammers used in the past, not so much anymore, where they wouldn't send any words in the message. They would just send a picture, and the picture would contain the spam message. So spam filters quickly learned that if the only contents of the message is just a single file, particularly if it's an image, then just flag it. And that's oftentimes why sometimes if you just send an image to someone without any text, it just goes straight to their spam box. Of course, if it's from you and you've sent them messages before, then it goes into their inbox. But if you just kind of unsolicited send your grandmother, say, a picture of a cat, and this is the first time you sent her just a picture, then it might go straight to her inbox or spam box and she'll never see it. How about if the message contains just a link? Just something for you to click on. That's a giveaway. A really common one is to include in the email message a very small image. In fact, so small you can't even see it. It's a 1 by 1 pixel image, usually transparent. So somewhere in that email message, there is a 1 by 1 pixel. You won't even see it, and it's transparent, so it just blends in with the background. And the purpose of this pixel is, to let the sender know that you opened the message. See, most email programs won't load the images in an email message unless the person opens the email. So if you're just looking at the list of messages, where it just has the list of the subjects and who it's from, it hasn't actually looked through the body of the message yet. When you click on that message, it then loads the message into the bottom part of your screen, and then any images that are included in there get loaded in as well, particularly if those images aren't part of the email message like as an attachment, but they are just a hyperlink, something for it to go fetch off of a web server. So it fetches from the web server this 1 by 1 image, which is transparent. And that 1 by 1 image has been given a unique file name just for you. It's just probably a random jumble of letters and numbers. But every single message has a unique file name for that. So when the spammer looks at their logs as to who has loaded that image, they can see who has opened up the email message and who has caused their mail program to load that image from their web server. And they know then who specifically opened that message, and therefore they're a person that they should probably send more messages to because they are more likely to open up messages and read them. These are called tracking beacons. And this is why a lot of email providers recommend that in your settings you have it set to not load images automatically, so that these little tracking beacons don't get loaded when you open up the message. In fact, I think on some email providers now, that's now the default. Images will not load automatically until you click a button to say load the images. So all of these techniques and more can be used as criteria to determine if a message is spam or not. Each one of them is assigned a score. And again, if the score goes over a certain threshold, then you'll mark it as spam. If it is under that threshold, you mark it as not spam and it goes into your inbox. And occasionally it makes a mistake, and then it's your responsibility to teach this what the correct answer was by moving it into the correct box. Okay, so that is the stuff about spam filtering and Bayes rule. So what we're going to do is we'll take a little break, and then we'll go over the homework assignment for this week. Okay? So any questions before we take a little break?
Yeah, is this the same logic that would be used in like a neural net?
No. Neural networks are basically a two-dimensional array of what are called artificial neurons, and they're connected together the same way the brain is connected, right? You got your nucleus, and you've got these axons and dendrites touching each other. So the neurons in an artificial neural network are set up kind of in a grid pattern with all these connections between them. and then you feed data in from one side, and those data go in and influence the numbers that are inside of these artificial neurons, and it produces an output. You know, an artificial neural network could be used as a different way of doing spam filtering, where basically you feed in the words and then those run through with some calculations, and it produces a yes or no answer on the output. So certainly you could use an artificial neural network to do spam filtering. That is probably actually a technique that's being used these days because the computational power is now fast enough that we can do that. But it's totally different, right? It's a totally different setup, totally different set of calculations. If you ever can, take a course in artificial intelligence at like a four-year university, I would recommend doing it. I mean, it's certainly very, very relevant to today's world. Back when I was in university, I took a course in artificial intelligence, and it was presented as like, yeah, this is kind of neat, but you know, here's some techniques. We got neural networks, we have genetic algorithms, we've got a couple other techniques. You know, it's kind of cool, but we haven't found like the really whiz-bang, this is what we're going to use artificial intelligence for. And we could already kind of see it being used a little bit in things like grammar checkers for your word processor, and in classification of things like words. So back then they were doing things like teaching computers about the world, to say things like, you know, sky is associated with the word blue and clouds and rain and sun, right? There's associations between things in the world, so then they could make new inferences about, like, you know, maybe you could have a conversation with somebody, like, you know, someone says like, oh, you know, the sky is really blue today, and then the computer would come back like, oh, you know, is it sunny? Right, so it would kind of know these things about the world, and it was projects back then to teach computers about these things. But now these days, computational power is so high, particularly when you use things like GPUs, that we can do these massive artificial neural networks that are much more complicated than they used to be back in the 80s and 90s. And now we can do things like image recognition, speech recognition, you know, golly, you know, there's a whole bunch of stuff that's being done now with artificial intelligence. So it just wasn't even possible back when I was learning about it. So I think it's just amazing. They call these deep learning because the neural networks are now just not like a grid of 20 or 30 neural networks. They're now grids of thousands of, not neural networks, artificial neurons, now grids of thousands of them. So the computations can be done really fast. And you can even get enough computational power on a little computer that costs like $5. You know, these little Arduino computers are built specifically to do things like image recognition and speech recognition. It only costs a few bucks. It's a huge difference from 30 years ago. For those of you who are watching on Zoom, I forgot to hit record. Again. Luckily, we have the YouTube recording, so you'll be able to watch that. Now, the problem is that doing the YouTube stuff is like another layer of complexity. So I hit record on the YouTube side, and then my brain thinks, oh, I've already hit record, and then it forgets to hit record on the Zoom side. I think what I need is a little checklist, a little piece of paper. It says, did you do this? Did you do this? Did you hit record? I want to look something up. So give me a minute to look something up. Be back in a moment. Okay, I'm just about there. Okay, so really quickly, the homework assignment for this week is simply to work out some of these probability questions. I have a probability homework that's in the form of a quiz, but it's not really a quiz. It's just a place for you to be able to do the calculation, type in the answer, and the computer will check to see if you got it right. And for some reason, it doesn't see my laptop here. Let's try that again. Well, that's something you'll have to fix here. So if you're one of my students, you can just go into Canvas, go down to the probability section. There's a homework assignment there. So there's 8 problems. You work through each one. Please answer, it'll tell you how many decimal places you need to round each number to. And then when you're all done, it'll check your answers and then tell you if you got them right or not. If you didn't get them right, it'll give you a link to a YouTube video that you can watch. It'll give you the solution to working out a very similar problem, probably with some different numbers. Every time you redo the assignment, it'll give you a different set of numbers, but basically the same questions. So you can do this as many times as you want, and then when you have got them all right, then it marks you as complete on the assignment. So that's basically it. I was going to show you the problems, but it's not, I can't bring my laptop up on the screen for some reason, so you'll just have to take my word for it. What I did want to do was tie in all this Bayesian stuff with some current events. Like, we got this COVID coronavirus thing going around, and it's been around now for a year and a half or more. But very early on in the whole pandemic, there was a need to find out, before we had a vaccine, before we had developed tests to find out if you have the coronavirus, but they were expensive and they took a long time. And so what some pharmaceutical companies worked on was a test to find out if you had the antibodies to the coronavirus. And if you've taken a biology class, antibodies are the cells that will fight off the infection. And there are basically 2 kinds. There's a IgM and IgG. I don't remember what the initials stand for, but basically one of those antibodies are ones that you develop while you are actively fighting off the infection. And the other one is one that you develop after the infection is already gone, and those are the long-term antibodies, the ones that remember what the invading virus looked like so that it can fight it off in the future. And some of these antibody tests only tested for the first kind, some of them only tested for the second kind, some of them tested for both. And so the FDA because they were trying to rush these tests through as quickly as possible so they get them in the hands of the public and the practitioners, was they were doing the emergency use authorizations, and they would publish on their website statistics about how well these tests work based upon information given to them by the pharmaceutical companies. So in developing the tests, the companies would then try these tests out on a sample of people and then see if they worked or not. So what they would probably do is they would take a blood sample and they would look under the microscope and see whether you actually had the coronavirus or not. So they would get some statistics about whether you have it or not, whether you have the antibodies to it or not, and then see how well that compares with their tests that they did. And they would publish these statistics, and you could get them. In fact, here it is. Right here is the authorized serology test performance. And back when I first looked at this, a little over a year ago, there were only about a dozen or so, 20 or so companies and their tests on here. Now there's hundreds of companies have produced these tests. And there are two kinds of ways to administer the test. There's one called lateral flow, and there was one back then called ELISA, E-L-I-S-A. The latter one, the ELISA one, is where they take a blood sample or whatever. They do something, probably a blood sample, and then they send it off to a laboratory, and the laboratory does all sorts of stuff to the blood sample and then determines whether or not you have these antibodies to the coronavirus. Those usually take anywhere from 3 to 7 days to produce the results. Those are really highly accurate tests. And then there's one called lateral flow, which is basically a dipstick, right? Maybe you put some blood or some mucus onto this thing, you dip it in the solution, and then those of you who are probably familiar with like drug tests or pregnancy tests, you either get a plus indicator or a minus indicator on the stick. It only takes a couple of minutes to produce the results from that. So you get very, very fast turnaround on those. Those were the preferred ways of doing these tests back in the early days of the coronavirus because they were so fast. And so I thought it was interesting to go through this list here, and here's what it looks like. You've got information here. Here's one from Abbott Laboratories, which is a well-known pharmaceutical company, and it tests for the IgG and estimate performance, 98%. And these numbers in parentheses are basically what fraction of their test subjects did it work on. And so 51 out of 52 test subjects the test worked on, and 1 out of 52 it didn't work on. Some words you need to know are sensitivity and specificity. We'll get to those in a moment. But one of the things I think is interesting about these statistics is the relatively small size of the people that they tested on, because there weren't a whole lot of people back then who had had the coronavirus that they could actually do these tests on. So their sample size tended to be fairly small for doing the positive test, and big enough for doing the negative test. That's why we got like 2,008 people for the negative test and only 53 for the positives, because they can only find 53 people that had coronavirus. Let me keep scrolling down to some of these others. And you can also see here what kind of tests they are. Here it says lateral flow. And if we scroll down some more, that's also lateral flow. This is like the most common kind of test, lateral flow. Again, kind of just a dipstick. And then here's one that's more like a blood test that they would do. You can see that these ones here perform pretty well, like 100%. But keep in mind the size of their samples, right? Only 29 people they tried it on. It's not a really big sample size. So you might have to take this 100% with a little grain of salt, a little skepticism that it really is 100% because their sample size was so small. So, like I said, back then there were only about 20 or so items in this list, and it was easier to scroll through the whole thing. But, here's one that was fairly common, this Biocan Diagnostics, Tell Me Fast Novel Coronavirus. IgM, IgG antibody test. So lateral flow, right? So quick results. And here's the sensitivity and specificity. I'll get into what those words mean here in just a moment once I can switch my screens. But one test is for the IgM antibodies, one test is for the IgG, and also there's a combined, right, test for both. So again, they're up in the 90s. Now, the sample size is not huge, but this was about as big as they could get back a year and a half ago. But you look at these numbers and go, this is pretty good. So let's take a look at that. So first of all, sensitivity means you got a positive test given that you have the disease. We call this a true positive. And specificity is a negative test given that you don't have the disease. This is a true negative. So we're going to look at Bayesian diagnostics. Just run the numbers. Okay, so we have the probability of you have coronavirus. We have the probability of a positive test given you have coronavirus. The positive of a negative test given you don't have coronavirus. And so these last two numbers we can get right off of their website. So we've got, for sensitivity, I'm going to use the combined numbers here. For the sensitivity, we've got 93.3% down here at the bottom. And then for the specificity, we have 96.2%. So those are the numbers I'm going to use. But what we don't know, or at least we didn't know back then, is what's the probability that you have had the coronavirus in the past? So we just kind of had to guess at this number. And we still don't really know this number, but let's assume that 5% of the population have had coronavirus. I don't know what the number is now. Like if we have 40 million, what is it, like 350 million people in the United States? And we divide it by, we don't actually really know how many people actually had it. You know, but if we say it's like 4 million people, no, not 4 million, maybe 40 million people, which is probably higher. That's only 11%. So, well, let's go with the 5% number. And remember, this is the 5% who have had it in the past. So we can work out the other numbers. The probability that you have not had it is 0.95. The probability of a negative test given that you have coronavirus or have had it is 0.067. And the probability of a positive test given that you don't have coronavirus is 0.038. And I want to know, what's the probability that you have had the coronavirus if the test comes back positive, right? So you go into a testing facility, you do their lateral flow test where they take some blood sample or swab or something like that, and they run this quick test. And we want to know what's the probability that you have had the coronavirus if the test comes out positive. So this sounds like a job for Bayes' rule. Let's go ahead and set up the table. So we got 0.05 and 0.95 for the prior column. And then under the plus column, we have plus given coronavirus, which we've got a number for that. It's 0.933, and then a positive given you don't have it, which is this number over here, 0.038. Then we're going to multiply across. And if I use my calculator, I get 0.05 times 0.933, and I get 0.04665. And then for the bottom row, I get 0.0361. Then let's add those together, and I get 0.08275. Okay, and then final probability, 0.04665 divided by 0.08275. 0.04665 divided by 0.08275, and I get 0.564. Okay, so you take one of these tests, and it turns out that if the test comes out positive, the probability that you actually have had the coronavirus is only about 50%. Now, here's the thing that I think is a little wild. These tests back then cost about $200 to take. And your chances of based upon a positive result is really not much better than flipping a coin. So you could literally just find a quarter, flip it. If it comes up heads, you have coronavirus, and if it comes up tails, you don't. And you would have saved yourself almost $200. So even though on the face of it, these tests look like they're really accurate, 93%, 96%, the fact that the very small population actually has the coronavirus means that these tests really are not much better than random chance. So I saved my money. I ran these numbers, and I went, this is crazy. I'm not going to go spend $200 on one of these things. Again, this was all like back before we had vaccines and stuff. Okay, so someone here says, according to known statistics, it's actually 13.8% have had the coronavirus.
Yeah.
Okay, so that means we could redo this problem. .138 probability of a positive given coronavirus that remains unchanged, and the probability of a negative given you don't have it is 0.962. So the probability that you don't have coronavirus is 0.1 minus 0.138, 0.862. And probability of a negative test given this remains unchanged, and so does the other number. How recent are those numbers? Like,
They
September?
pulled the total number of cases and U.S. population off of Google, just a Google search, right?
So hopefully like from September or October, something like that. Okay, let's set up our same table. Let's see how this changes. Okay, 0.138 times 0.933 is 0.129. And then 0.862 times 0.038 is 0.0328. We'll add those together. Zero point 1618. So because more people have now had the coronavirus, the accuracy of that test goes up to about 80%, which is better than the almost 50% we had before, but it's only because you're more likely to have had the coronavirus now than you were in the past. You're 3 times more likely to have had it, and therefore these numbers go up a bit. So the tests are getting more accurate as the number of people who have had it go up. You know, at some point the test will become nearly 100% accurate. If everyone in the world has had the coronavirus, then the test will be almost totally accurate, up to about 93%. So still, if you have to choose between, if you're taking one of these tests, if you have to choose between a lateral flow or the more comprehensive ELISA or CLFA test, I mean, opt for the latter because that one's going to be a lot more accurate than these lateral flow ones. These ones are really designed to just do really fast results, but they're not very accurate at all, even though the percentages seem to be pretty high, 93, 96%, ultimately because of the prevalence of the disease in the population, the actual probabilities are fairly low. So you have tools now to be able to evaluate these sorts of numbers when they come out. You look at these numbers and you go, wow, 93, 96%, that's really accurate. It's not at all, or it may not be, because you've got to factor in these other calculations. So with Bayes' rule, you can do some of these calculations yourself. And in fact, if you go back to that website, they've actually worked out some of these numbers. These numbers used to not be here on this page, but now they've worked it out. So if the prevalence is 5%, then PPV, which is the positive test, is only 56%. That's the number we came up with. But it's 99% accurate if you don't have coronavirus. But then if we go up to, well, we're now close to 15%, we can see the number is right now here at about 81, which is pretty close to what we calculated. Right? Our calculation is 14%, so we got about 80%. So we're pretty close. So the FDA has gone and worked out some of these numbers to see how the accuracy of the test changes as the prevalence of the coronavirus increases in the population. So, pretty cool stuff, I think. Someone posted a question saying that the YouTube videos at the end of the quiz weren't working, and I went through and I fixed that. I think what happened was YouTube went through and found so there's 3 ways to publish a video on YouTube. There's public, which means anyone can watch it. There's unlisted, which means if you have a link to the video, then you can watch it. Otherwise, if you do a search, you won't be able to find it. And then there's private, which means only the owner of the video can watch it. And so I have a whole bunch of unlisted videos because, I only want people in my classes to watch it because they contain solutions to problems, or because I don't want people to search for the video. I want them to just be able to have a link to it. And I think YouTube went through and they found all the unlisted videos and they set them to private because they've added on some more security features. Secure meaning like, you know, make sure that people aren't watching the video who aren't supposed to watch the video. And so they went through and they just said, we're going to make all the videos private, and then you can go through and make them unlisted again if you then go through the process of answering the additional questions we have about the video. And so I went through and I marked those videos as being unlisted, and they should now work. So you can now, when you get to the end of the quiz, you can click on the link or copy and paste the link into your browser, and then you can watch the video that gives you the solution to that problem. Okay, I think that's it for today. We are moving on to the next unit next week. So we're done now with probability. I don't remember what the next thing is. I think it's probably graphs, I'm guessing. Oh, I can look on my laptop. I should do that. Yes, we're starting with graphs next time. So we've only got, what, 5 or so more weeks, 4 weeks left in the semester. So we're going to do graphs for a while. It'll take about a week and a half to do. Then we're moving on to finite state machines. And then that'll take us almost to the end of the semester. And then we'll have a couple of days at the end where I kind of like have nothing scheduled. I usually put those in as kind of like slack space, so that if I get sick or if there's some unscheduled days when school is not in session, then I got some space to move things around. But it looks like we're going to finish up a little bit early, and so there's an opportunity to talk about some topics that aren't on the syllabus. We could do things like explore more how compilers and interpreters work. We can do quantum computing. We could do more problems. We'll dive deeper into some of the topics we've talked about over the course of the semester. We got a whole bunch of stuff we could do. And so as we get closer to that time, I'll figure out what we can fill the time with. Or you can give me your suggestions. Post a comment or post in your discussions like what you would like to see maybe on those last couple of days, and then we'll do those. And of course, we've opened up a little bit of time this semester because we don't have any tests, right? Don't have a final exam. So during that exam week, we've actually got time to do stuff. All right, that's it for today. That's all I got for you. Any questions before we take off?
I don't think so.
No, we're good. Everyone's good. I'm looking at the chats. Anyone here? Everything's good. It's been pretty quiet on the YouTube side. If you get a chance, come in on my C programming live stream. That's a lot more active. A lot more going on. We're working. Remember, we were doing cracking passwords a couple weeks ago. We're currently doing that in my C class. So they're writing programs to crack passwords, kind of like you guys did in Python, but now because C is compiled and can run faster than Python can, we can work with much bigger dictionaries. Dictionaries with 3 million words in it.
Cool. Thank you.
All right. That's it for today.
Thanks, Professor.
Thanks, Professor. Take care.
You're very welcome. Have a great day. Bye-bye. All right, now the Zoom people are gone. Now I have to get to the YouTube people. So I hope you did enjoy it. There wasn't a lot, like I said, not a lot of chat going on, but interesting stuff about Bayes' theorem and how it applies to current events and how you can run the numbers yourself and evaluate whether you think people are telling you the truth or not telling you the truth about how effective their tests actually are. All right, bye YouTube audience. I'll see you later. Take care.